are ready for another exciting video. Tonight your homework is a handout, and it is available on Canvas. And I want you to practice some throwback skills to AAF and the beginning of this year, where I asked you to solve some trig equations. Notice the domain that I'm giving you is including 0 but not including 2 pi. So if you want to pause the video and try some of these on your own, I'm going to go through them quickly since they are prerequisite knowledge, right? My job is to isolate x. So using the order of operations backwards when you're solving, right? I'm going to get rid of addition and subtraction, get rid of any multiplication or division, and then undo sign, all with inverse operations. So x is going to be equal to add 1, divide by 2, take the inverse sign of both sides, right? So who has a sign of 1/2, positive 1/2 on my unit circle between 0 and 2 pi, right? That would be pi over 6 and 5 pi over 6, right? Do the same thing here, except again I'm getting 3x by itself. So I'm going to add 1, divide by 2, inverse cosine both sides. Oh crap, I still have to get rid of that multiplication by 3 now. So who has a cosine of 1/2, and then divide that by 3. Cosine of 1/2 would be positive pi over 3 multiplied by 1/3, so that's pi over 9. Cosine's positive in the 4th quadrant, so that would be 5 pi over 3 multiplied by 1/3, so 5 pi over 9. This time I have to collect my sine x's, so I get 2 sine x is equal to negative root 2. Now x is going to be negative root 2 divided by that 2, and I inverse sign both sides, right? So who on my unit circle has a sign of negative root 2 over 2, or negative 1 over root 2? If I hadn't rationalized, sign is negative in both the 3rd and 4th quadrant, and root 2 over 2 goes with a pi over 4 issue, right? So pi over 4 in the 3rd quadrant, and pi over 4 in the 4th quadrant. Okay, so I don't just do that for no reason. There must be a reason why we had you practice solving trig equations, right? Am I right? Am I right? Because you're going to need to solve polar systems, right? Solve polar systems need you to remember how to solve trig equations, because our polar equations are involving trig, and the reason you need to do that is because you've got, right, to solve a system, going back to your Algebra 1 and Algebra 2 and pre-cal, when you solve a system, you are looking for points of intersection. So solving polar systems means I want to find points of intersection. You're going to have to interpret those systems graphically, so that's going to use some knowledge from yesterday or the previous video where you were, am I dealing with a circle, a limacon, a cardioid, a spiral, or whatever. And then the only thing that's weird is, what do these common points mean? So this should be points of intersection, right? I have some prior knowledge to that. Interpret, right, the graphs, right? Multiple graphs, since it's a system. It's just common points that's a little weird. So the first example, solving polar systems, notice I've bolded the word solve, and I've bolded and made red intersection points. And then I have this weird looking icon at the bottom. Call this a phantom. Okay, so let's just deal first with some prior knowledge, right? Solve a system to find all intersection points. Notice that I've included 0 and not included 2 pi. And the first thing I want you to recognize is, even without my calculator, r equals 4 is a circle. What is r equals 4 cosine 2 theta? Right. Previous knowledge, that's a rose with how many petals? 4 petals with a length of what? Good. So even without my calculator, I can certainly go to the circle of 1, 2, 3, 4 and draw my circle with radius 4. And then using my knowledge from the previous lesson, since this is a cosine rose, I know I'm going to have 4 petals and they all line up really nicely with my Cartesian axes, right? And my length is 4. So this one, I started with this one because I hope you can see that this circle and rose do meet places, right? But the expectation for solve is that you are using algebra to find intersection points. Algebra goes with intersection points. So let's solve this system simultaneously. That's going to be important to you. Simultaneously solve. I think I'll solve this by substitution. If r is called 4, I think I will put 4 here and solve for theta. Inverse cosine both sides. I'll write this once, but that's about it. So who has a cosine of 0? Again, on this interval. I'm sorry, who has a cosine of 1 on this interval? And that is 0. And the inverse cosine of 2 theta is just 2 theta. So theta equals 0. And now I do need to think about, since I wasn't just talking about theta, taking the cosine of theta, I was taking the cosine of 2 theta. 0 might not be my only answer on 0 to 2 pi, right? So what if I put pi in here? I know the cosine of pi is -1, but if I put pi in for theta, 2 times pi is 2 pi, and the cosine of 2 pi is also 1. So I actually have 2 algebraic answers from solving a simultaneous system. So I found theta, so I have an r comma 0 and an r comma pi. What is that radius, right? You go back here and plug in, well, gee, my radius is constantly 4. So certainly these are my 2 intersection points. And yes, I know I can name this other, right? I can name this with a negative radius, right? But I'm going to name it that way. And just to verify, go ahead and let's look at what happens when we plug in those points into my system, just to check, right? If I check my answer, right? Well, certainly there's no theta to plug in here, and I get 4 both times, right? So check, check. But what happens when I plug 0 into here? Cosine of 2 times 0 is the cosine of 0, which is 1, and 1 times 4 is indeed 4. What happens when I plug in pi to the second equation? 2 times pi is 2 pi. The cosine of 2 pi is 1. 1 times 4 is indeed 4. So I checked, and both of these are points of intersection. Points of intersection come from solving a simultaneous system. But you can clearly see that there are other points where these two graphs meet. And this is the difference between simultaneous and not. Remember, polars is a fancy way of doing parametrics. And parametrics has the third parameter of time in it. And so does polars. Let's go to that calculator so hopefully you can see what's going on a little bit better. So, in your calculator, remember yesterday I told you, or the previous day, I told you to change your mode not only to polar but to simultaneous. Then in y equals, I want you to put 4, the circle 4. Over here, put the rows, 4 cosine 2 theta, and go ahead and change also to your bubble graph. Whoops, sorry, I went too far. Let me check my window. 0 to 2 pi, small theta step. Right, my total length is going to be 4, so I should be okay with all of these settings. And look at what happens when I graph simultaneously. Can you see what's happening? Boom! Let me do that again. Look at those bubbles. Right? Watch those bubbles go. Let me turn this off, and let me turn this back on. Watch when the bubbles meet. They met at the beginning. They meet, boom, they meet. Boom, they meet. Those two graphs met. They got to the point 40. They both started at the point 40. They were there at the same time. Both equations, both graphs were there at the same time. But notice here, at 4 pi over 2, sure, I'm there on the first circle, but not at the same place at the same time. Here, 4 pi. On both equations, same place, same time. Nope, not same place, same time. That's the difference between a point of intersection and a common point, or as some people call them, phantom points. Right? So you are responsible for finding points of intersection with your math, and you are responsible for finding phantom points with your graph, right? So with your calculator and your graph. So the phantom points are here. And it doesn't matter how you label them, which equation you label them with. Given a choice, math books will always use the positive radius as long as it keeps them within their theta within the given range. So phantom points are your common points. And our common points were right there. Okay, so this one was pretty easy to see. Sometimes they're not always easier to see. Not always as easy to find. But you do need to recognize the difference, and that didn't happen to us in rectangular form. A point of intersection was a point of intersection. We always called them solving a simultaneous right system. We always said they get right at the same time. The same point satisfies both equations. But if you notice, Both of these common points satisfy the first equation, but look what happens when you plug pi over 2 into here. Cosine of 2 times pi over 2 is the cosine of pi. The cosine of pi, right, is -1, and -1 times 4 is -4. Now, sure, I can rename, right, points, but that's what they mean, right? You can't plug these points into both equations and they satisfy them. This location, though, is in common to both graphs. This location is in common to both graphs, but the coordinates don't satisfy both equations at the same time. So, graph the system to find the common points. Solve to find the intersection, graph to find the common. So let's try another one like that. I don't know why those are there. So notice the real directions would be graph the system, then find the intersection points, but remember the expectation is you do this with algebra, and common points with the graph. So first I'm going to take care of intersection points. I'm not even going to look at the graph. So I'm going to solve this system with substitution by putting r is equal to 1 plus 2 sine theta in for this r here and get 3 minus 2 sine theta. And collect my sine thetas and move my numbers over here. So sine theta is equal to 1/2. So I'm going to inverse sine. Who has a sine of positive 1/2 on the interval 0 to 2 pi not included, and theta is equal to pi over 6 and 5 pi over 6. So my points of intersection are r comma pi over 6 and r comma 5 pi over 6. What is the radius? We'll go plug in pi over 6 to either equation and you're going to get the right radius, right? Pi over 6, sine of pi over 6 is 1/2. 2 times 1/2 is 1. 1 plus 1 is 2. Sine of 5 pi over 6 is also 1/2, right? 2 times 1/2, right? Or if I put it here, pi over 6, 1/2. 2 times 1/2, right? And 3 minus, so 2 times 1/2 would be 1, and 3 minus 1 is 2. So these are my points of intersection. Now I know that both of these are Limassol, right? Because I have, right, an add and subtract here of what in rectangular would be the would be the sinusoidal axis. So let's look at our graph. Right, this is a Limassol where I have this is a loopy Limassol, right? Because my sinusoidal axis is at 1, but I'm going to go up to 2 and down to -1. So this is a loopy Limassol that points which way? Points up. This is a regular Limassol, right? Because my sinusoidal axis is at 3 and my amplitude is 2. So I'm going to go up to 5 and down to 1, but not hit the x-axis, so I don't kiss the curve. So it's a regular pole. So this is a regular Limassol, but it points down. Right? Big radius is 3, little radius is 1, big radius is 5, little radius is 1. So I say all those things not because I was asked to, but because if I graph something incorrectly, I'll know it, right? Watch, meet. right? See how often do they cross? 2. So did you see they simultaneously got to the same place twice? Those are my 2 points of intersection. Do I have a common point? Did you see someplace else where they met? They had the same, it was a point in common, but that location isn't a point of intersection that satisfies both equations at the same time. Right? There. I hope you can see it is right, which I kind of knew. Both of them had a small radius of 1, right? So I can name that common point -1, 3 pi over 2. But in truth, again, given a choice, a mathematician, math people, math books, math answers are all going to give a positive value. So again, I'm going to make a pathetic drawing here. Right, I had the 5, 1, 2, 3, 4, 5. So I had the no kissing limaçon that way, and then I had the loopy limaçon this way. Right? So 2 points of intersection, 2 pi over 6, right? That's kind of 2 pi over 6. And 2 5 pi over 6. And then a common point here of 1 pi over 2 that I just found by graphing. And again, I could kind of tell from there. Okay? Again, look how terrible my graphs are. They're not great. Not going to judge you, right, on how good or bad your graphs is, and probably most of you will put my graphs to shame, and you'll do a really nice job. I'm terrible. But the focus is on the math of the intersection point and the graph as it relates to finding your common points.